Welcome back to this explainer. If you're an engineering student gearing up for that brutal linear algebra exam, especially if you're currently tackling video 8 of the Matematica series, well, you're in exactly the right place. Today, we're going to master one of the absolute most powerful tools in your mathematical arsenal. We're talking about determinants. Honestly, think of the determinant as the ultimate matrix cheat code. It's this single, magic value that completely unlocks the secrets of a system of equations before you even begin the heavy lifting of solving it.
Zero. Just nothing. Take a second and just sit with that number.
So what does this single digit actually tell us? Let's dive in. Imagine you're handed this massive, super complicated system of equations. Instinctively, you might just roll up your sleeves and start doing tedious row elimination to see if it can even be solved. But what if finding just one diagnostic number meant you could skip all of that? If that one number turns out to be 0, the entire nature of your system fundamentally changes. It's an absolute game changer for saving time on your exam.
So what exactly is it? Well, by definition, the determinant is a single real number calculated from a square matrix, and it brilliantly illustrates this really profound physical concept. For a 3x3 matrix, the determinant actually represents the volume of the parallelopope, basically a 3D geometric shape that's spanned by the matrice's column vectors. But here's the most important part for your exam. This volume instantly tells you if the matrix is invertible. If the volume is 0, the shape is literally collapsed flat, and there's no way that matrix can be inverted.
Here's our game plan for today. First, the ultimate matrix cheat code. Then, our toolkit, Sarrus and Laplace. Third, we'll look at the zero determinant trap. Fourth, the boss fight, the 4x4 matrix. And finally, a quick recap and how this actually applies to engineering.
Okay, moving on to part 2, the toolkit, Sarrus and Laplace.
First up, take a look at the visual simplicity of the rule of Sarrus. By just copying the first two columns over to the right side, you simply multiply down the main diagonals and add them up, and then you multiply up the reverse diagonals and subtract them. It's fast, it's rhythmic, and it's highly visual. But, and listen to me closely here because this is a crucial exam survival tip, this rule strictly only ever works for 3x3 matrices. Seriously, if you try this on a 4x4, you are going to instantly lose points. Don't do it!
And that brings us right to our next tool, the Laplace expansion. This one is your universal master key. See that plus-minus checkerboard pattern? To use Laplace, you just pick any row or column. You take each number in that line, apply the plus or minus sign from the checkerboard, and multiply it by the determinant of the smaller submatrix that's left over when you cross out that number's row and column. It's really elegant. It beautifully breaks down any massive matrix into smaller, much more solvable pieces.
So the real trick is knowing exactly which tool to grab from your belt. You're going to want to use the rule of Sarrus when you're staring down a standard 3x3 matrix and just need a fast, reliable answer. But the very second you face anything larger, or maybe a matrix that's packed with variables instead of numbers, you've got to pivot to the Laplace expansion. It's the only way to reduce the dimensionality step by step.
Moving right along to part 3, the zero determinant trap.
I like to think of this as the chain of doom. In linear algebra, these mathematical statements are completely locked together. If the determinant is 0, it automatically means the columns or rows of your matrix are linearly dependent. Basically, they're just multiples of each other. And because they're dependent, the matrix has no inverse. Because it has no inverse, the system of equations has no unique solution. It's a total domino effect. If an exam question feeds you just one of these facts, you instantly know the other 3 are absolutely true.
Spotting this trap early will save you a massive amount of time. Just check out the matrix we have here. The first column is 1, 2, 3. The second column is 4, 5, 6. But look closely at that third column, 3, 6, 9. Wait a second, that's literally just the first column multiplied by 3. Because those columns are proportional, they are linearly dependent. Boom! You don't need Sarrus, you don't need Laplace, you can literally just write down determinant equals 0 and breeze right on to the next question.
All right, part 4, the boss fight, the 4x4 matrix.
Listen, if you try to jump straight into a Laplace expansion on a 4x4 matrix full of random numbers, you're going to end up calculating 4 separate 3x3 matrices. It is an absolute arithmetic nightmare. So here is our battle plan. First, you hunt for any row or column that already has zeros. Second, use elementary Gauss operations, like adding a multiple of one row to another, to force even more zeros into that specific line. And finally, you expand using Laplace right along that zero-heavy line. Let's look at a real example from the source material, matrix C. It's a pretty daunting 4x4, but look at our strategy here. The top row has a 2 and the third row has a -2. By using a really simple Gauss operation, just adding row 3 directly to row 1, we create a brand new top row. We end up with 2, 6, 0, 0. We just force 2 zeros right into the matrix. And remember your golden rule here. Adding a multiple of one row to another does not change the value of the determinant.
So now we deploy our Laplace expansion along that newly modified first row. And because of the zeros we just cleverly created, 2 of our submatrix calculations are completely wiped out. They just multiply by 0 and vanish. That massive, scary 4x4 boss fight instantly collapses into a highly manageable problem involving just 2 smaller 3x3 matrices, which you can easily solve. It's all about working smart, not hard.
Finally, Section 5. Recap and engineering application.
Okay, here's your rapid-fire exam survival guide. Number 1, always check your matrix size first so you pick the right tool. Number 2, apply the rule of Sarrus exclusively to 3x3s. Number 3, always scan your columns and rows for obvious multiples so you can catch that linear dependence zero trap. And number 4, if you face a 4x4, force some zeros using Gauss operations before you ever attempt a Laplace expansion.
Now, you might be wondering, why does any of this actually matter outside of a stuffy exam hall? Well, because in your future career as a civil or structural engineer, these matrices represent real physical systems. When you build a model of a bridge's structural load, it generates this massive system of equations representing physical forces. If the determinant of that system is non-zero, the math guarantees there's one unique, stable solution for those forces. The structure holds. But if the determinant is 0, the system is unstable or unsolvable.
The determinant isn't just some abstract number you calculate for a grade. It is literally the ultimate diagnostic test for the stability of the physical world you're going to be designing. So I want to leave you with this. The next time you face a massive, intimidating system of equations, whether that's on a math test tomorrow or in an engineering simulation years from now, will you just dive in and blindly calculate, or will you check its determinant cheat code first? Good luck on your exams, everyone, and keep learning.